So in this video, we're going to be looking at some examples of some molecules and how to first determine the Lewis structure, then determine the shape, and then determine the hybridization around central atoms in the molecule. Our first example here is H2CO. This is formaldehyde. When we look at a molecule, the first thing we should look at for that molecule is how many valence electrons we have. In H2CO, the carbon brings 4 valence electrons, the oxygen brings 6 valence electrons, and the hydrogen brings 2, or 2 total. There's 1 on each of the hydrogens. So 2 plus 4 plus 6 is 12. So what that tells us is that in this molecule, we get to play with 12 valence electrons total. Now, when we set up our molecule, our central atom, we identify it by looking for the least electronegative element in the molecule that traditionally is typically the center, and additionally you can't ever have hydrogen being a central atom. So in this case it's carbon. So we have carbon as our central atom, and the 2 hydrogens are beside it, and the oxygen is beside it too. Now our first step now is to bond everything. Make sure that there are 2 electrons between all of the atoms that are bonded. We've now used 6 electrons. 6 electrons are in our structure. 2, 4, 6. Therefore, we started off with 12. Now we only have 6 electrons left to play with. All right, and we add them now to the most electronegative element first, which would be oxygen. The most electronegative element that is not fulfilled in terms of the octet rule or the duet rule, which would be oxygen. So we add them to the oxygen first. 2, 4, 6. We're now out of valence electrons. We can no longer add any valence electrons to this problem. Now, when we look at the rules, the duet rule, it refers to hydrogen, and hydrogen has 2 electrons by it. That's good. This hydrogen has 2 electrons by it. That's good. Oxygen obeys the octet rule. It needs 8. 2, 4, 6, 8. It has 8. Carbon also obeys the octet rule. 2, 4, 6. It's missing some. It wants to have 8 around it. It only has 6. In order to fix that, what we must do is share more electrons between atoms that are happy and the carbon. And the only place this is possible is from the oxygen. So we're going to take one of the extra pairs on the oxygen, let's say that pair there. Instead of having it being a lone pair on the oxygen, we're going to move it into a position sharing those pair with the carbon, so that both of them get to see those 2 electrons. That therefore makes a double bond. And now if we look, carbon sees 2, 4, 6, 8 electrons, and the oxygen sees 2, 4, 6, 8 electrons. The octet rule is satisfied for everything. We can redraw our molecule slightly more appropriately with lines for bonding electrons. So we have the carbon, single bonds to both hydrogens, a double bond to the oxygen, and there's 2 lone pairs on the oxygen. Now, one final thing we should make sure of in these structures is we should look at formal charge to make sure that all the atoms have the correct formal charges, and we've minimized the formal charges. So, hydrogen, according to the periodic table, has 1 valence electron. And remember that in formal charges, an atom gets to see half of the bonding electrons. So it sees half of these 2, therefore it sees 1, and therefore its formal charge is 1, the number of valence electrons it wants on the periodic table, minus 1, the number of valence electrons it has in the structure, or 0. The same with the other hydrogen, also 0. Carbon, according to the periodic table, wants to have 4 valence electrons around it. And in our structure, what we see is it gets half of all the bonding. So it gets half of these 2, so 1, 1, 1, 1. 1 plus 1 plus 1 plus 1 is 4. It wants to see 4. It sees 4. Therefore, it has 4 minus 4, 0 as the formal charge. According to the periodic table, oxygen wants 6 valence electrons around it. And in this structure, it has 2, 4, because lone pairs are totally counted by the atom. So it gets to see both of these, both of those, and then 1 of this from this bond and 1 from that bond. So 2, 4, 5, 6. It wants to see 6. It has 6. 6 minus 6 is 0. It has 0 formal charge. All those formal charges are very small. They're 0, can't get much smaller, and therefore this is our good final structure. And now we can start analyzing for shape. And to do that, remember, the first thing we look at is we find our central atoms. In this case, we have a central atom, carbon, our central atom. And around that carbon, we have 1, 2, 3 regions of electrons. All right, 3 regions of electrons, that means that we are in the trigonal planar family of shapes. How many bonded atoms do we have? Well, we have 1, 2, 3. So with 3 regions and 3 bonded atoms, our final shape is indeed trigonal planar. That's our shape for this molecule. Now we can look at hybridization. Hybridization has everything to do, and only to do, with regions of electrons. And if I look at the carbon, hybridization, all atoms and bonded molecules are hybridized except for hydrogen. It's the only one you don't got to worry about. So in this case, we have to worry about both carbon and oxygen. So we look at regions of electrons. So first around the carbon, how many regions of electrons? 1, 2, 3 regions of electrons around that carbon. And with 3 regions of electrons, that means we need 3 hybrid orbitals. What I mean to say is 3 regions needs 3 hybrids. And what gives that? What gives that is sp2. Right? If we look at sp2, that means I have 1s and 2p that have been hybridized for a total of 3 atomic orbitals. And remember, when we add atomic orbitals to hybridize them, the number of atomic orbitals we add equals the number of hybrids we get out. So since we added 3 atomic orbitals, we're going to get out 3 hybrid orbitals, which is what we need. So for the carbon, we know that the carbon is now sp2 hybridized. Now for the oxygen. Again, regions of electrons for the oxygen. All right, we have 1 region here, 1 region there, 1 region there. So 3 regions around the oxygen. So again, 3 regions. What does that tell us? That tells us we need 3 hybrids. And that tells us the oxygen must be sp2 hybridized. So now we know the shape, the actual Lewis structure, we know the shape itself, and we know the hybridization around each of the atoms in it. Let us take a look at another example. Xenon tetroxide. All right, this is a molecule of xenon, a noble gas. And again, the first thing we have to do is count up the valence electrons. According to the periodic table, xenon brings 8 valence electrons and oxygen brings 6, and there are 4 oxygens, so the 6 multiplied by 4, and you do the math, and what you find out is that in this molecule we have 32 electrons that we're going to be adding in this structure. The central atom in this case is the least electronegative element, which in this case is xenon. So we put xenon at the center, and we put some oxygens around it. And there we see that. Now, the first thing we have to do is bond everything. So I'm going to add in electrons to bond to make bonds where I know bonds must be. I've now used 8 valence electrons, so I have 24 remaining to add. I add them to the most electronegative element, which would be the oxygen. And I do this systematically: 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. I'm out of valence electrons. And it appears, if you look at this, that everything's all sorts of satisfied and happy, right? Because xenon has 2, 4, 6, 8 valence electrons around it. Each oxygen has 2, 4, 6, 8. Everything looks great. But just to be sure, we still need to do formal charges just to make sure. So, formal charges. Oxygen. According to the periodic table, oxygen wants 6 valence electrons. In our structures, it gives to see all the lone pairs, so 2, 4, 6, and half the bonding, 1. So 2, 4, 6, 7. It wants 6. It sees 7. 6 minus 7 is minus 1. So each of the oxygen has a formal charge of minus 1 because they're all identical. Xenon, according to the periodic table, wants to see 8 valence electrons. How many does it currently have? Well, it gets to see half the bonding electrons. So 1 from here, 1 from there, 1 from there, 1 from there, 1 plus 1 plus 1 plus 1 is 4. So it wants 8, it only sees 4, therefore it has a formal charge of plus 4. And now we see that there's a big problem with this molecule. We have a split charge. We have a lot of them, actually. We have a positive 4 at the center and minus 1s on the outside. That's not going to be very stable. In order to rectify this problem, what we can do is start moving electrons. You see, each of the oxygens has 1 too many electrons it's seeing. But if it shifts one of its lone pair to a bonding position, it doesn't see one of them, but it'll see the other one, which will reduce its formal charge by 1. So what we're going to do is we're going to take a look at each of these, and we're going to take this one, remove the pair from here, and add the pair as a bonding pair. We're going to take one of the pairs from here, remove it from there, and add it as a bonding pair. Remove one of the pairs from there, add it here as a bonding pair. And finally, at the very bottom, remove that from there, add that there. Now, what you immediately notice is that Xenon, in total, is seeing a heck of a lot of electrons, way more than 8. 2, 4, 6, 8, 10, 12, 14, 16. But that's okay. Xenon's large. Xenon can have expanded octets. So we're fine. And if we look now at our formal charges, the xenon has a formal charge now. If you calculate it wants to see 8. It actually sees 8, 0. Each oxygen wants to see 6. They're seeing 6. They're all 0. So by doing this, we've reduced the formal charges on the oxygen. We've increased the formal charges, or changed the formal charges at the center, and therefore we've minimized our formal charges. And so now we know what our final structure actually looks like. The xenon is at the center and is double bonded to 4 oxygens. Each oxygen has 2 lone pairs on it. And so this, then, is our final structure, our final correct Lewis structure for this molecule, xenon tetroxide. So now we begin to look at shape. In this case, we only have one central atom, xenon. And what we look at, remember, first off, we look and we see how many regions of electrons does the xenon have around it. It's got 1 region, 2 regions, 3 regions, and 4 regions. 4 regions, that tells us we are in the tetrahedral family of shapes. How many bonded atoms does it have? 1, 2, 3, 4. 4 bonded atoms. So I'm in 4 bonded atoms. So if I know that I have 4 regions and 4 bonded atoms, then I can look it up, and I find out that this shape is indeed named the tetrahedral shape. This molecule, in other words, is tetrahedral. Now we look at hybridization. All the atoms in this molecule hybridize. None of them are hydrogen. The oxygens all hybridize the same because if you look at it, each oxygen has a double bond to it, each oxygen has 2 lone pairs. So really we're only talking about figuring out the hybridization of the xenon and the oxygen because all 4 oxygens are identical. Let's start off with the xenon. The xenon has 4 regions of electrons, 1, 2, 3, 4. 4 regions of electrons, and remember how we did this in with the last example. That tells us that we need 4 hybrid orbitals. And what has 4 hybrid orbitals? Well, that is the sp3 hybrid. Remember, I need 4 hybrids, so I must have 4 atomic orbitals, 1, 2, 3, 4. So sp3. So the xenon is sp3 hybridized. Now what about the oxygen? Each oxygen has 1, 2, 3 regions of electrons around it. So 3 regions, and therefore we know that we need 3 hybrids. And what has 3 hybrids? sp2. So each of the sp2, or each of the oxygens, is sp2 hybridized. Great. Now we can move on to our next example. PO33-. Again, just like we've done over and over now, we first have to figure out how many valence electrons we have. All right? So we find the periodic table, we look up phosphorus. Phosphorus has 5. Oxygen has 6. There are 3 of them. So 6 times 3. Now the -3 only tells us we have 3 extra valence electrons. So we just add an extra 3 electrons to cover the -3 charge. And now we know that we have 26 valence electrons to play with. What's the central atom? Well, in this case, it's the least electronegative element always. In this case, that's phosphorus. So phosphorus is at the center, and there are 3 oxygens around it. First, we bond everything, putting 2 electrons between all the atoms that I know are bonded. I've used 6. Now I'm down to 20 electrons left. Adding them to the most electronegative element first, oxygen. 2, 4, 6, 8, 10, 12, 14, 16, 18. I've got 2 more electrons I've got to put somewhere, and I can put them then on the phosphorus, because the phosphorus was unsatisfied, you see. So here's my seeming structure. Now, one thing we got to make sure of is we need to check this to make sure formal charges are all working out nicely. So, for the phosphorus, according to the periodic table, phosphorus wants 5 valence electrons around it. How many does it have? Both of these, it's 2, 3, 4, 5. It has 5 around it. It wants 5. It has 5. Its formal charge, therefore, is 0. What about the oxygens? They want, according to the periodic table, they want 6 valence electrons. How many do they have? 2, 4, 6, 7. Each one of them has 7. 6 minus 7 is -1. So each oxygen has a -1 formal charge. Now you might be thinking, well, that seems bad because we have not all zeros. Well, that's perfectly fine. You can have not all zeros. You just want your charges, your formal charges, as small as possible, and you don't want split formal charges. You don't want a charge on one atom to be totally the opposite sign as a charge on the neighboring atom. And we don't have that. We have some -1s, we have some zeros. They're all small, and yes, they're negative, but they have to be negative. Some of them have to be negative because it turns out that some of the formal charges, when you add them all up, all the formal charges must add up to the total charge on the molecule. So -1 plus -1 plus -1 equals -3, which is the total charge on the molecule. Hey, that's always good, right? So now we know our structure is correct. So we draw it with lines to make it sort of look, as a formal Lewis structure with lines for our bonding. And what do we see? We see this. Single bonds to each oxygen. Each oxygen has 3 lone pairs, and the phosphorus has a lone pair of its own. All right, so now we can start looking at shape. Our central atom in this case is the phosphorus, so we look around it. How many regions of electrons does it have? Well, it has 1 region, 2 regions, 3 regions, 4 regions. So I know I have 4 regions around my center. And 4 regions tells me that I'm in, like the last slide, the tetrahedral family. Unlike the last slide, however, each phosphorus, the phosphorus is attached, has bonded to it 1, 2, 3 atoms. So I'm bonded to 3 atoms. So it has 3 bonded atoms. So what do I know? I know I have 4 regions of electrons and 3 bonded atoms, and if I look up what that means my shape is trigonal pyramidal. That's my molecular shape. Now I need to actually look at the hybridization of each of the atoms that aren't hydrogen, and I've got oxygen and I got phosphorus. Note each of the oxygens again are the same, so I don't have to do it once because they're all the same. So first, phosphorus. How many regions around the phosphorus? 1, 2, 3, 4. So I have 4 regions of electrons. And that tells me, as we've done before, that I need 4 hybrids. And what has 4 hybrids? sp3. So the phosphorus is sp3 hybridized. What about the oxygen? Each oxygen has 1, 2, 3, 4 regions around it. And once again, 4 regions means 4 hybrids. And 4 hybrids means it's sp3. So the oxygens also are all sp3 hybridized. So now we've completed this problem. SCN minus. Once again, we start off as we always start off. Number of valence electrons. The sulfur has 6, the carbon has 4, the nitrogen has 5, and the minus sign tells me I have 1 more. So plus 1 more. When I add up all that, I know that I have 16 valence electrons that I've got to deal with in this problem. So the central atom is carbon, and the sulfur and the nitrogen are beside it. Bond everything. 2 electrons there, 2 electrons there. I've used 4. I'm down to 12 left. Add them to the most electronegative element that is unfulfilled. Well, right now they're all unfulfilled, but the most electronegative element of these is nitrogen, so give them electrons first. 2, 4, 6. I have 6 electrons remaining. Now look to the next most electronegative element, that's sulfur. Give it the electrons next. 2, 4, 6. Now I'm out of valence electrons, I can't add any more dots. And when I look, while the sulfur has enough valence electrons around it, and the nitrogen has enough electrons around it, the carbon doesn't. It only has 4. It wants 8. So I've got to start shifting some stuff, making double bonds. So one thing I can try, take a pair of electrons from the sulfur and put them as a double bond, and take a pair of electrons from the nitrogen and make them into a double bond. And remember that even if we do this, once we look at the formal charge will tell us whether or not we're right, because you don't want split charges, and we can fix that then. So what do I have right now? Right now I have a structure, carbon, double bonded on each side. On one side to a nitrogen with 2 lone pair, on the other side is sulfur with 2 lone pair. So now I do formal charges. Carbon wants 4 valence electrons according to the periodic table. How many does it have? 1, 2, 3, 4. 4 minus 4 is 0. The formal charge on carbon is 0. Nitrogen. Nitrogen wants 5 valence electrons according to the periodic table. How many does it have? 2, 4, 5, 6. It wants 5. It has 6. 5 minus 6 is minus 1. Sulfur. Sulfur wants 6 valence electrons. How many does it have? 2, 4, 5, 6. It wants 6. It has 6. Its formal charge is 0. And this then is a very good structure. One thing we do notice we should look for and make sure of is that when we do have we do have a negative charge, we notice that that negative charge is on the most electronegative element in the structure, and that's something that's required. You don't want a negative charge on an atom that has a very low electronegativity if you have the option of putting it on an atom that has a very high electronegativity, like this one does. That means that this structure is our final good structure. The sulfur double bonded to a carbon, double bonded to a nitrogen, the nitrogen having 2 lone pairs, and the sulfur having 2 lone pairs. And one thing I think I forgot in the last example is because it's its charge, one thing we should do is put square brackets around it with the charge on the outside to indicate that we do indeed know that this is an ion. Now we look to the shape around my central atom. My central atom in this case is carbon. It has 2 regions of electrons around the carbon. So 2 regions. And that tells me I'm in the linear family. I also note that I have 2 atoms bonded to my central atom. So I have 2 bonded atoms. So 2 regions of electrons, 2 bonded atoms. This is a linear molecule. So that's its shape. And now hybridization. This time we have 3 atoms to worry about: sulfur, carbon, and nitrogen. And let's do carbon first. As I mentioned a moment ago, carbon has 2 regions of electrons around it. 2 regions for hybridization, that means we need 2 hybrids. And what has 2 hybrids? If it's 2 hybrids, I need 2 atomic orbitals, and what has 2 atomic orbitals? The sp hybrid. So this is sp, so this is the carbon is sp hybridized. Now, what about the sulfur? Sulfur has 1, 2, 3 regions around it. 3 regions. And as we know from previous examples, 3 regions means that we need 3 hybrids. And what has 3 hybrids? The sp2 hybrid set. So that's for sulfur. Looking at nitrogen now, it has 1, 2, 3 regions. So again, 3 regions. That means we need 3 hybrids. And that means what we have is sp2 for the nitrogen. So the carbon is hybridized sp, the sulfur is hybridized sp2, and the nitrogen is hybridized sp2 also. So now we've taken care of all of that. Our next example is SF4. And we approach this exactly the same way as we've done before. All right, first, number of valence electrons. Sulfur has 6. Each fluorine has 7, and there are 4 of them, so 7 times 4. So doing that math, we find out that we have 34 electrons that we're going to be playing with in this problem. The central atom is the least electronegative, which in this case is sulfur. So sulfur goes in the center, and my fluorines go around it. And there I have them. Now, we bond everything. 2, 4, 6, 8. I've now used 8 electrons. I'm now down to being able to having 26 electrons remaining. I add them starting to the most electronegative element first, and in this case, that's fluorine. So, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. I have 2 left. Now, the fluorines can't have any more electrons. They're in row 2. The octet rule is absolute for them. They cannot have more than 8. So I've got to find a place to put these 2, and the only place I can put these 2 is on the sulfur. It can handle expand octets because it's in row 3. So I put 2 more, a lone pair, 2 electrons on the sulfur. Rewriting this to make this look a little simpler to read, you have the sulfur, it's singly bonded to 4 fluorines. Each fluorine has 3 lone pairs. And the sulfur has 2 lone pairs of its own on the sulfur. Now, looking at formal charges, we look at the fluorines and the sulfur, and we have basically 2 sets. All the fluorines are the same. So, fluorine wants 7 valence electrons. How many does it have? Each fluorine has 1 pair, 2 pair, 3 pair. So 6 in the pairs, plus 1 there, that's 7. It wants 7. It has 7. Therefore, the fluorines have no formal charge of 0 for all of the fluorines. Sulfur, according to what the periodic table says, sulfur wants 6 valence electrons. How many does it have? Well, half of the bonds, 1, 2, 3, 4, and all the lone pair. 2 more, that's 6. It wants 6. It has 6. Therefore, its formal charge is also 0. So our structure is good. Our structure is then done. Now, shape-wise, what is the shape that we have here? Around our central atom is sulfur. How many regions around the sulfur? Well, 1, 2, 3, 4, 5 now. So we have 5 regions around our central atom. And that means we are in the trigonal bipyramidal family of shapes. How many bonded atoms? 1, 2, 3, 4. 4 bonded atoms. So we have 5 regions and 4 bonded atoms. And what's that tell us? That tells us our shape is the seesaw shape. We have 2 types of atoms in this molecule that we have to worry about, sulfur and fluorine, for our hybridization now. So starting off with the sulfur, how many regions? 1, 2, 3, 4, 5, just like I said a moment ago. So for hybridization, I have 5 regions, just like I just said. That implies I need 5 hybrid orbitals. And what has 5 hybrid orbitals? That means I need 5 atomic orbitals, so I need dsp3. So my sulfur is dsp3 hybridized, right? 1d, 1s, 3p's, that's 5 atomic orbitals, therefore it gives me 5 hybrid orbitals. That's how you know that you're right. Now for fluorine. Fluorine has 1, 2, 3, 4 regions around it. So each of the fluorines have 4 regions. Therefore, I need 4 hybrids. And what has 4 hybrids? The sp3 set. So I have each fluorine being sp3 hybridized, and the sulfur being dsp3 hybridized. KrF2. Once again, starting the same way. How many valence electrons? Krypton has 8. Each fluorine has 7, and there are 2 of them. So we have a total of 22 electrons. We use our central atom is the least electronegative, which would be the krypton. So we have krypton in the center, and we have fluorine around it. And the first thing we do is we bond everything. I've now used 4 electrons. I'm down to 18 left. Add them to the most electronegative element first. Fluorine, 2, 4, 6, 8, 10, 12. I've now used 12. I have 6 left. I can't add any more to fluorine. Fluorine is in row 2, as I said, and therefore the octet rule is absolute. So I have to add it in the only place I can, which is krypton. Krypton being not in row 2, being way below row 2, way down in row, 4, it can have expanded octets, and therefore it can handle more than 8 electrons. So we start adding them there. 2, 4, 6, and I'm out of valence electrons. So now, at this point, we have a structure, and we should look to our structure for formal charges. So fluorine. Fluorine wants 7 valence electrons around it, according to the periodic table. How many does it have? 2, 4, 6, 7. 7 minus 7 is 0. So each fluorine has 0 formal charge. That's good. Krypton. Krypton wants 8 valence electrons according to the periodic table. How many does it have? 2, 4, 6, 7, 8. 8 minus 8 is 0. Krypton also has 0 formal charge. Therefore, we know our structure is good. So what do we have? We have the krypton singly bonded to the fluorine on each side. Each fluorine has 3 lone pairs, and the krypton itself has 3 lone pairs. All right, now we can talk about shape. Our central atom is krypton. How many regions of electrons are on the krypton? 1, 2, 3, 4, 5. I have 5 regions, and that, remember, tells us that we are in the trigonal bipyramidal family of shapes. How many atoms are bonded? 1, 2. 2 atoms are bonded. So I have 2 bonded atoms. So, with 2 bonded atoms and 5 regions, what's my shape? If I look it up, my shape is linear. Now, for hybridization. I've got 2 atoms I've got to deal with, krypton and fluorine, and both the fluorines are the same, so we'll start with krypton. How many regions? 1, 2, 3, 4, 5. 5 regions. And for hybridization, we now know what that means. 5 regions means 5 hybrids. and 5 hybrids means what I have to have is dsp3. So my krypton is dsp3 hybridized in this structure. Fluorine now. It has 1, 2, 3, 4 regions. Each fluorine has 4 regions of electrons. 4 regions means 4 hybrids. And what has 4 hybrids? The sp3 hybridization. So the fluorines are sp3 hybridized. I hope these examples have helped you better understand how to go from formula to Lewis structure, check your Lewis structure using formal charges, determine the shape around the central atoms, and then determine the hybridization of each of the atoms that is not hydrogen.